This instruction is on free body diagrams. The steps that we will go through, number one, is to isolate the part to be analyzed. In the first case, we're going to analyze this L bracket. We will sketch a stick figure of that and identify everything that's touching it. We see that it's touching something at B, D, A, and C, and capital letter each of those contact points. So that's been done. And then categorize each type of connection. Notice that at B, it's resting on a roller. And at D and C, there are applied forces. And at A, there's a smooth pin. And then what you need to do is replace each of those contacts with the reactions that they can furnish. Notice that a roller, here is how a roller behaves, and a roller could look like any of these connections. And the way it behaves, notice that all it can do is hold the roller or the object from penetrating the surface. In other words, it furnishes a force perpendicular to the surface and to resist penetration. Notice it cannot hold the object down. It doesn't have the capacity to hold it down, and it cannot furnish a lateral force, and it can't furnish an amount of moment. It can't keep it from rotating. So what happens at point B to our object is a force like that. We'll call that force B. The reason we letter these is so that we can refer to the forces. So that's force B, and that's the only way it can act. Here is the applied force at D, and that's 200. If you know the amount, instead of writing the letter, you can write the amount. At point A, there's a smooth pin. The way a smooth pin acts is it can furnish a force in any direction, but it can't furnish a moment. It cannot keep the object from rotating, but it can keep the object from moving in the X direction or in the Y direction. So what I would always suggest is that you always put this in the first quadrant. We don't know what direction that pin is furnishing the force. So we will put this, we will call this AX and AY, and we'll put that here on our object, and always put it in the first quadrant so that it's an unknown, so we'll assume the positive direction. And then we have the 100 pounds acting like that. So that's what the free body diagram would look like for that L bracket. Now let's do this cart that's resting on a surface. When you do the stick figure for this, we're going to draw the whole cart. So the whole cart will include all the way down to the bottom of the rollers. So we're going to draw a stick figure, and it's going to include all the way down to the bottom of the rollers. Notice that what's attached to it is a cable. The only thing, and this is the indication of a cable, the only thing a cable can do is pull along itself. It can't push, it can't cause rotation. So you will always have a force. Oh, sorry, we didn't label our. Let's call this A, B, and C. And notice this one is labeled for us. It's already labeled G. That's the center of mass. So we're going to have a cable, and it's going to pull along itself. So what you know is the angle. If you're given that angle, that would be exactly along that cable, and that's force C. Here's the roller at A, and here's the roller at B. Now the other thing you have, if they show a center of gravity, if you do not assume a massless object, if the center of gravity is shown or assumed to have mass, then what happens there is that you will have a vertical force down, a vertical force downward, and an amount of that is the weight of the object. That weight is equal to its mass times the acceleration of the center of the acceleration of gravity, not the center of gravity, the acceleration of gravity, which is 32.2 feet per second squared, or 9.81 meters per second squared. I always write this as mg, just to remind myself that if it's a mass, I have to multiply it by g. So that's what the free body for that cart would look like. Now, if we have a free body, if we have an object that has more than one more than one part, notice we have a ball and two links and a cable. The first thing you have to do is decide what you're going to draw, what parts you're going to draw. Let's label, several of these are already labeled, A, B, C, D. Let's call this contact right here F, and this contact right here G. So now we have them all labeled. Let's say the first thing, and here's the center of mass of the ball. Oops, already called it G. Let's call this GH. Let's call that G because that's the center of mass. So first let's draw the ball. So you draw the ball. Here's its weight, that's mg. And the other thing touching it is the roller type effect. Now, if that surface has friction, I'll show you how that works. If that contact has no friction, then the only thing it can do is just hold it to keep from penetrating the surface. If the surface has friction, then it can hold it to keep it from penetrating, and along the surface hold it to keep it from sliding along the surface with an amount equal to the force of friction. We'll assume these are frictionless surfaces. So that would be force F, and this would be force H. So that's what the free body diagram of the ball would look like. Now, if we wanted to draw, if we wanted to analyze what's going on with pin C, notice we didn't even see pin C. So in order to do that, we would have to draw one of those links, one of those objects that's holding the ball up. So let's draw ACHE. So there's our stick figure. Here's A. Two things can happen at A. There would be a surface. The surface is touching it. Let's call this A. And notice it's vertical only. And then here's the cable. Now, that cable, let's call it AB, because the other end of it would also be AB. Here's a smooth pin. That's going to be CX and CY. And now notice that it's also being touched by the ball that we've already drawn. Now, Newton's third law says that for every action there's an equal and opposite reaction. That means that in order for this link to put a force on the ball like that, then the ball has to put a force on the link exactly equal and opposite. So right here where that contact is made, that looks like the right direction, that would have a force, and you label it H as well, because those two are equal and opposite. So that's how you account for more than one part and the fact that those are internal forces. Now the other thing we can do is draw the whole thing. We can draw this entire thing. We can enclose this entire thing in a box. And when you do that, all of those forces that we've already drawn, all of these and all of these, most of them are internal forces. Internal meaning that inside this system, this is called a frame, by the way. It's called a frame. Inside this frame, there's a balancing H is being balanced by reaction H, so they're all canceling each other out. CX and CY are being balanced. If we drew BCFD, it would have a balancing force. So those all cancel each other out internally. So the only thing you see when you draw that entire box are the external forces. The only thing touching this from externally is the gravity, is G, force G, and the two surfaces forces, A and B. So that way, this becomes a very simple analysis. Notice that A and B are each half of G because it's symmetric. So, so you would instantly know those values if you were trying to solve for those values. So that's how you treat more than one object when you have a frame that has more than one object. Now, the other way that you can have more than one object is called a truss. You identify a truss being different from a frame because all of the connections are smooth pins, and all of the forces are applied at those smooth pins. Now, the other thing about the way this makes a truss distinct is that all of these members, A, B, BC, and so on, are called two-force members. Now, the nature of a two-force member is shown right here. The fact that all it has to support, the only forces on this two-force member are two smooth pins, means that those two smooth pins will not have, remember before we said a smooth pin could have an X and a Y? If that smooth pin is attached to a two-force member, the only thing that two-force member can conduct or apply is a force along itself. It can't furnish any forces except along itself, and that's what this is representing. So if we drew the force on pin A, well, pin A, all of these are two-force members. So if we drew the force on pin A, let's just isolate the pin. Our stick figure is actually going to be a dot, and that dot is pin A. The only thing pin A is touching is the world. It's being supported here by the ground, so it will have an AX and an AY coming from the ground. And the other thing it's touching is link AB, which is a two-force member. So it will also have a force that we're going to call AB. A two-force member is very specialized, and so we're going to give it a two-letter designation to represent the two ends of the two-force member. And you will always show that as if the two-force member is in tension. That's the sign convention for a two-force member. Notice if AB is a rubber band and it's in tension connected between A and B, it would pull on pin A. Now, what that does for you is that if you go up here and draw pin B, if this is pin A, if we draw pin B then pin B would have an equal and opposite reaction AB on it. It would also have BC, BD, and BE. So that's how you draw, and that's called a truss. And in analyzing a truss, you end up drawing the pins in order to analyze all the forces. Now, what you can also do is you can enclose this entire truss. Oh, by the way, that had a 3 kilonewton applied force on it too. Sorry, left that off. You can also put this entire thing in a box and analyze and draw that as a stick figure. So if you draw that entire box, all of those that I just drew, all those ugly little spider-looking forces are internal now. So the only thing touching it is the world at AX and AY, and the world at B, BY and BX. That's a smooth pin. That's the world. That's not a two-force member. It's not attached to a two-force member. It's attached to the world. And then the applied forces, the 3 kilonewtons and 3 kilonewtons. Notice that we've assumed all these are weightless, do not have weight. So that's how you draw a frame. A truss. That's a truss. Now, if you have something rigidly connected, like this connection at the wall, or if you cut through and try to look at this cross section AA, the way you have to represent that is in this designation, is that wall can furnish not only an X and a Y force, but it can also keep that, this is the first one that we've seen, it can also keep that cantilever beam from rotating off that wall. So if you drew the stick figure for the L bracket, let's just draw that, and if we drew what's going on here at A, we would have to show it as furnishing an AX, an AY, and a counterclockwise moment. Counterclockwise is considered positive for applied moment, and then the two forces applied 300 and 500. So, and if you wanted to analyze it here at cross section AA, it would look the same way. It would just be shorter. This would be cross section AA. It would have AX, AY, and a different amount of moment, MA. Let's call this M little a, call that M big A, because those would be different amounts of moment. And this would be 300 and 500. So that's how you have to draw. That's called a rigid connection. That's how you'd have to draw that. Now let's look at how you would treat a pulley. The nature of a pulley is if it is a frictionless pulley, and if it is free to rotate without friction, then these two cables that go around it have the same amount of tension in them. If this is amount T, then that's an amount T. Now the way you can treat that is that you can actually, without worrying about how far away that radius of that pulley is, you can simply take off the pulley completely and apply those two forces, these two tensions, each equal to each other, at the pin of the pulley. So you simply take this tension and move it down to the pin, take this tension and move it up to the pin, but you have to keep them oriented in the direction that they were originally oriented. So if we wanted to draw the pin of this pulley, then that pin would have, let's call this connection, we already have an A, let's call this connection D, where it's connected to the ceiling, to the wall. So that pin would have a DX and a DY, because it's a smooth pin, DX and DY coming from the world. And then it would have a tension, let's call this T, going down at a known angle, T, 70 degrees to the horizontal, and another equal amount T, going off at 24 degrees. So that's how you would draw that pin. And then if you drew the beam, it would have an AX and an AY. It would have a T coming off at point B. The applied force P, some weights hanging on it, and another T coming off at point C.